Thank you so much for having us. I really appreciate it. By the way, are you still working? Are we disturbing you? I feel like you're disturbing. So I try to not disturb you. Hey there. Oh man, that's amazing. Hello. My old friend Debezium OG Sergey from Schubert's here.
Yes.
That's amazing. Thank you so much for being here. Thank you all for being here. All right, so let's get started. The idea is we want to talk a little bit about change stream processing with Apache Flink and Debezium, and to set the scene a little bit. Well, all this is motivated by the realization that the world around us is happening in real time, right? So people place purchase orders like continuously. If you have like a wind turbine, it sends measurements continuously to us. If there's credit card transactions, this happens in a continuous infinite stream. It doesn't happen in batches, right? So reality around us, this happens continuously. And now the IT systems which we built to model this reality, this also should work in real time to give us the most value out of our data. And the core thought there is, well, the older data is, the less it has value, right? Just to give one example, if I'm in a financial scenario and I want to do something like fraud detection on a real-time stream of credit card transactions, so I want to look for patterns of abuse. So like my credit card is being used right here, you know, in Santa Clara in this minute, like the next minute it's used in Hamburg where I live at home. This probably is like a abusive pattern, right? So we want to detect this and lock down this credit card. And now you only can do this in a meaningful way if we have the fresh data. So if you look at the transactions from yesterday imported to us by a batch, this won't get us very far, right? So the older data is, or the fresher data is, the higher its value is. And today we would like to talk a little bit about this real-time data in the context of databases and reacting to changes in databases in real time with change data capture and this project called Debezium, which I'm going to talk about. And then also taking this data and making more sense out of it, reasoning about it using Apache Flink. So that's the part which is Robert gonna cover. And then we will do a demo of those two things together, motivating more the use cases, and hopefully all this is gonna work out. Before I hand it over to Robert, a few words about myself. So as Chester mentioned, I work as a software engineer with Decodable. Great startup. If you want to do stream processing, check us out. Before that, I've been working as a software engineer with Red Hat. So I've been there for exactly 10 years, and I used to be the project lead of Debezium. And well, this is why I'm talking here to you today. By the way, who is knowing about Debezium? Okay, those guys. Okay, who is using Debezium? Like, oh, yes, very good. Few brave souls, very good. Awesome. Great. So then, Robert, I would hand it over to you.
Yeah, thanks a lot. So I'm also working as a software engineer at Decodable. I am one of the original creators of the Apache Flink project. I'm in the PMC there. And I started or helped make the Flink project open source in the context of a company that we've started. It's called Data Artisans, was later renamed to Verica. We exited this company to Alibaba a little bit too early. Yeah, I'm now working at Decodable to make Flink and stream processing accessible to wider audiences. So I am first going to introduce Flink now in a general introduction talk, and then Gunnar is going to connect the dots with change data capture. And if you have any questions, please interrupt me. It's a small group, and I want you to go home and have learned something today. So please interrupt me. Let's make this interactive. I am going to drive the conversation by explaining you this sentence. Apache Flink is an open source stream processing framework for low latency, high throughput, stateful, exactly once, distributed, and time-aware workloads. So I hope that at the end of this talk, you will have an understanding for each of these words here on the slide. So let's start with the first two words. What is Apache Flink? Apache Flink is an open source project at the Apache Software Foundation. It's one of the biggest projects there in terms of mailing list activity, like user questions, developer communication, commits, pull requests, Jira tickets, and so on. It enjoys a really wide industry adoption. I don't think you need to tell you that Flink is very popular as a stream processing framework. So where is it used? Here's an example architecture of a, I don't know, like customer 360, whatever use case that I made up. So let's say you're in a support center and you want to be able to quickly look up all the data you have about one particular customer, like your mobile phone provider, and you want to know how was the reception of my user in the last 24 hours. So the end result is this real-time dashboard that is constantly updating as more data is arriving in our system. And I just have like a bunch of data sources here, like an application server here that is receiving some real-time events straight into Kafka topics like the clicks and impressions on this application. I have legacy systems like a data warehouse. I have the actual like production data, like the transactional database. All this is streamed with Debezium as change streams. And then we use Flink to consume these events from Kafka topics, join the data, aggregate the data, and then write this whenever something is changing. Like whenever there's new information coming into this architecture, Flink will update the data in Elasticsearch, which is serving this dashboard in real time. So this is the high-level perspective of where Flink fits into application architectures. So this is too much text, but the idea is to explain you where do you use Flink. And the upper half of the slide is use cases where Flink is part of the architecture, like end-to-end applications, like real-time alerting, fraud detection, analytics, IoT data processing, inventory management, and so on. The upper half of the slide is how Flink is used in these architectures. So let's say data pipeline building blocks. So you can use Flink for data routing, filtering, aggregations, building sessions, like you want to analyze how users behaved on my website in a browsing session. So you can see it's a really rich framework that can cover a lot of use cases. So we've explained what Apache Flink is, and we've explained the workloads that you can do with Flink. Let's now move on to the foundations of stream processing with Flink. Like what are the basic ingredients in Apache Flink that enable us with these use cases or to do these use cases? And I'm going to talk about three underlying primitives: events, state, and time. And you're processing events in a data flow. A data flow consists of a data source, let's say Kafka, Kinesis, Debezium for CTC. Then we have an aggregation and a data sink. And Flink is taking care of executing this data flow efficiently in a cluster. So it knows how to distribute this problem onto multiple machines, and you can scale it up and down as your workload is changing. So if you're running this on two worker nodes, they're called task managers in Flink. Flink will translate this logical data flow representation into a distributed execution graph, which will run efficiently on the cluster. Then there's state, and state is, for example, in case of the data source, the current offset of the input Kafka topics, or in case of Debezium, like the current transaction log, whatever identifier. Then in an aggregation, it's the current aggregates, like count per key, like if you want to count the number of activities per customer ID or something. And then for the data sink, there's also some metadata about the transactions. And Flink is guaranteeing that this state is durable. So if you're killing one of your nodes in your cluster, if something is going wrong, then Flink knows how to recover the state from a state backend, like from a state storage. And this is usually S3 these days, used to be HFS back in the day. And Flink also guarantees for the state exactly one semantic. So if something goes wrong, Flink knows how to restore your state so that it seems that you're not processing data twice. Like all your counting, all the data that you're sending downstream to Kafka will not produce any duplicates. And the state is stored in pluggable state backends. So you can actually grow your data that you have in your cluster beyond your available main memory. So if you have like 16 gigs of memory in your cluster, you can still keep state like 100 gigs or so by storing it on disk. The third primitive that I want to talk about is time. Because in stream processing, you often have events that are arriving out of order. For example, because there's network disruptions, mobile devices are not always online. So events are arriving out of order in your stream processor. So imagine you want to window your events, like you want to collect these events into time buckets. And here I have an example where I collect the events from 9 a.m. to 10 a.m., from 10 a.m. to 11 a.m., and so on. Flink is aware of the time when this event has been created, not the time when this event is arriving at the system, because it could happen that it takes a long time from when the event was created until it actually ends up in our stream processor. Like the mobile phone was not connected to a network because we were in a tunnel or on an airplane or something. But if my use case requires me to do correct counting based on the time when the event has happened, the time handling features of Flink allow you to do that. So the window operator will collect these out of order events, like it will buffer them into the state of Flink, into these hourly windows. And the question now is, how does Flink decide when the window is complete? Because these events are just arriving randomly at different times. But at some point, I need to decide when all the events have arrived. Like otherwise, your latency you would wait forever until you see the result of your computation. And for that, Flink is using like a virtual clock for the event time. So periodically, there are some special events in the stream that tell the system how time has progressed. So in this example, there's a watermark for 10 a.m., which means that we have received all the data for the 9 a.m. to 10 a.m. window. So this means we can take the contents of this window and analyze it, because we have a guarantee that no events that belong to this window will arrive. And this decision is depends a bit on your data, like depends on what you know about your application, like how much delay you're willing to tolerate. And finally, I want to talk about ways of using these three abstractions, like events, state, and time in Flink. And there are two main APIs in Flink. The Flink SQL API is very easy to use because you just write like a SQL query, and Flink knows how to translate the SQL query in a very efficient execution graph and using efficient data types and so on. And there's like a low-level expressive API, the data stream API, that allows you to really define what to do with these events, how to react to time, what to store in state, and so on. And here are two examples of how these APIs look. So this is Flink SQL. On the left-hand side, we are defining a Kafka source. So we're defining the schema of the data in the topic. We're defining how to connect to the Kafka broker. And on the right-hand side, we are building a tumbling window. So basically what I've showed in the slide earlier, where we collect data for like an hour, this is what we are doing here in this example as well. We are collecting data for 1 hour and counting the number of elements that have arrived in the system. And this is the opposite, like this is the low-level API in Flink, the process function. Here you have access to all the raw ingredients in Flink. So here you see, for example, this value state type, which is backed by Flink state backend. So this the data that you put here can grow really large. It's not limited by the available heap. This method here is called, like process element is called on every event. There is this context object that you can use to operate on the event time, like the virtual time. And then there's this on timer callback that you can use for doing, let's say, asynchronous processing based on event time, like when you want to clean up your state, for example, after an hour or something. So now we've established stream processing framework and stateful. I'm now going to talk a little bit about this checkpointing algorithm, which is used to achieve exactly one semantics and to make sure that state is not lost in Flink. Are there any questions? Okay. Huh?
Sounds good.
Good. Yeah.
Good stuff, man.
I just want to make sure that it's interactive. Need to break the ice. Okay, so the naive approach of creating, or the goal of checkpointing, is to get a copy of all of the state of all the operators in my Flink job. And a simple approach would be to stop processing data, to make a copy of the state of each operator, like of the Kafka offsets, of the window contents, of the sinks, and so on, and then continue with the processing. We need to stop the processing, otherwise the count in the aggregation would be off. The problem with this very naive approach is, of course, that we would interrupt the processing. This would lead to high latency, and also, like, some of this cluster would be idle because we're not processing all the time. So the more efficient approach is to do a distributed checkpointing that is basically creating this checkpoint while the processing is still going on. And the beauty of this algorithm is that we can create a consistent checkpoint without stopping the actual processing. And this works by the central checkpoint coordinator telling the sources to start a new checkpoint. This means that the sources are writing their state into the durable state storage, like S3. So the state has been written to S3, and now the sources will send a special event downstream. So these red blocks there, they are special checkpoint barriers, and these barriers basically indicate to the operator that they have to, or like downstream operators, that they have to create a checkpoint. So now the barriers have arrived at the aggregation operator. So this operator is also backing up its state. And here you see that there's like a small representation of the job graph. And here we are basically tracking the state of these operators to complete. So now we have created, like, the barriers are arriving at the sink, and we've created a complete, consistent copy of all the states of the operators in a cheap, durable storage. And in case something goes wrong, we can reset the state. So by this, we can fairly cheaply guarantee that we can restore from a failure. So this is what I put for high throughput, low latency, exactly once stream processing. Now let's talk about the distributed aspect of Flink. So a Flink cluster consists of a job manager, which is the central coordinator that is managing the execution of the Flink job, and many task managers. So the task managers are basically the component that you're scaling up or down depending on the workload. And this is like really the most basic what is called a Flink cluster. So it comes in many shapes. For example, when you're using the Flink Kubernetes operator, you submit a custom resource into your Kubernetes and then the Kubernetes operator is picking up this resource definition and deploying a cluster for you in Kubernetes. So you're specifying things like the Flink version that you want to use, the resources for the job manager, the number of task managers, the resources for the task managers, and so on. And this is all managed for you in Kubernetes. So if you want to get started with Flink, this is my recommendation. You just need a Kubernetes cluster, install the Kubernetes operator, and then you can create as many Kubernetes Flink clusters as you need. So to summarize deployment, the Kubernetes operator is, in my opinion, right now, or in my observation, the most popular and recommended deployment option. It allows also to manage the state in your job, so you can suspend the execution, which will make the operator orchestrate creating a save point. And it allows upgrading the cluster, like you can change the job that you're running on this cluster, or you can just migrate to a different infrastructure, for example. It supports auto-scaling, so it will track the metrics of your Flink application and adjust the number of instances for each operator depending on the workload. Like if your job is basically not able to keep up with the incoming amount of data, then it will scale it up. There's a lot of other deployment options actually, so you can also just roll your own with like bash scripts and Docker, or you use Hadoop Yarn. So I learned on the conference there's still people using Yarn. So these components are basically, so this is basically the internal communication inside Flink of how a job, like how's your program code distributed in your cluster. So you're writing your Flink SQL here, or you're writing your Java data stream code, and then Flink is running an optimizer in the SQL case, or a data flow graph builder, and this job graph is then sent from this Flink client to the job manager. And this job manager knows how to translate this logical data flow graph into a distributed execution graph. So this distributed execution graph from the job manager is then distributed to the task managers to perform the work. So if you have like 2 Kafka sources, they will be placed in these task slots. If you have aggregation operators, they will be placed here. And once you've submitted this job, the job manager is constantly monitoring the health of these operators. So if the machine of one of the task managers is failing, the job manager knows how to restore these tasks back into the slots and knows which state to use for these operators, like the window contents, the Kafka offsets, and so on. To wrap up, I'm way too fast. So I also want to quickly talk about the like open source Flink and the open source community, because this is a very large community, very diverse, and often people ask me like, how do you contribute? How do I get in touch with the community? And the Apache Software Foundation is mostly based on mailing lists and mailing list-based communication. So there's a development mailing list where contributors and developers are discussing the roadmap of the project. They are discussing proposals, what to improve on the system, new features, when to do releases. And then there's a user mailing list where you can ask questions about the system. We recently launched a Slack instance where you also can ask questions. Then there's, of course, Stack Overflow and so on, meetups like this, conference like Current, and so on. The current version of Flink is 1.17, and 1.18 is coming next. And I think that's it. So now is your chance to ask questions.
Any questions?
Gunnar, what's your, okay, yeah.
Yeah, thanks, Robert. Actually, that's really good. I just had a question about, like, you know, the underlying platform of Flink is really good on the streaming. and processing on top of Flink, right? How about the ecosystem on top of it? Like I think one of the things I say, like CEP, the complex event processing, does it Flink in both provide that capability or provides connectors so that the other CEP can be embedded there?
So Flink has a CEP library that is a part of the project. So you can do complex event processing with Flink on top of the data stream API and also on top of Flink SQL. So in Flink SQL, it's called match recognize, but it allows you to basically have state machines that track your status or whatever in CEP. Yes.
Okay. I haven't checked the CEP from Flink, but thanks for that.
Yeah. So there is a machine learning library for Flink. There's all these windowing operators. There's a CEP library. There's, for example, also like Apache Beam, which is using Flink as an engine underneath. So there's a very rich ecosystem around Flink.
The one I used last is like 50 minutes. The one I used last time was
City.
City,
Yes.
WSF City.
Yeah.
Which basically have a rich set of transformations capability.
So I think there's a like GitHub repository for City on Flink.
Yeah.
There was another question here.
Yes. So you mentioned, because this confused me when I started. Well, so this is about the thing which confused me when I started. So there's two kinds of operators. There's the Kubernetes operator, and then you mentioned just other operators within the query. And maybe you just can expand a little bit on that.
Yes. So in Kubernetes, there's the concept of Kubernetes operators, which are working on custom resource definitions. So the Flink operator knows how to deploy Flink clusters, or the deployment operator knows how to run, like how to spin up pods based on Kubernetes deployments. And in Flink, there's also a concept called operators, like the windowing operator or the source operator or the like CEP operator. So this is like double use of this name and concept. Yeah. There's one question here.
So what would be a hello world sort of project that on the one hand could be easily installed in some simple environment like Minikube, which at the same time could help understand all the power of things, something less trivial than, I don't know, counting words or something.
Yeah, so I think one nice thing you can do is use this Flink CDC connector project with Flink SQL. So Flink has a interactive SQL shell that allows you to submit Flink SQL jobs to a Flink cluster. And then you can do, you can define like these CDC sources using SQL. And then,
Don't give away my demo.
yeah, okay. So we will all see how this is being done. And then you can run queries against the CDC scripts, which I think is pretty nice. Like you can then do like a real-time join. Like you can,
Like in a formal database?
yes, but it's a real-time join. So we will fetch like the snapshots of both tables and then continuously stream updates. So if you're doing an update, you immediately send output from Flink. And you can stream this, for example, into Elasticsearch or into Kafka or Redis. I think that's a nice use case because you can do these real-time joins, you can do basic aggregations on the data or filtering. Yeah. Very easily allows you to come up with more complex Flink jobs than just simple windowing or like simple workflow. Yeah.
So I would just do it with Docker to play around with. No need for Minikube in that case. So if you just want to play locally, there's no need to have Kubernetes.
Yeah, there's a lot of options to run Flink. So you can also another way to get started, let's put it like this, is to create an empty Java project, add the Flink dependencies, and then just run it from the main method. It will start like an embedded instance of Flink locally in your JVM, and then you can programmatically explore. Write a little data generator, and then use the data generator from SQL to analyze the data. Or you can also connect to Kafka, if it's available to your development machine. But it's a very neat way of exploring Flink if you're coming from a developer perspective and less from an operational perspective.
Cool. Thank you, Robert.
So should we
should we do a break or keep going right away?
We probably just keep going.
Okay. Cool. People want to get home. Relate to that. All right, Robert, thank you so much. This was great. By the way, I didn't see any questions from the folks in the back there. I'm disappointed.
What's your favorite color?
Yeah.
I was gonna offer another method for the test, Robert.
All right, so let's talk a little bit about Debezium and what this is about. So just to get back a little bit to start of the talk. So I mentioned we want to, get the most value out of our data. So we want to have real-time data. And by that, I don't mean like real-time in terms of, your computer sciences, like the hard limit, but real, like should happen like with a reasonably low delay, like, I don't know, seconds or milliseconds. So instantaneous, let's say. So we want to have real-time data. And in this context, it's about data which we have in typically a relational database, or maybe something like MongoDB, like document store. But this is the primary source of our data. And now we would like to reason about that data and as it changes with a low timely latency. So that's what we want to do. And Flink, as Robert alluded to, this helps us, of course, doing all those stateful processing operations, right? So we can take change event streams and join them, filter them, aggregate them, do all the windowing stuff. But of course, first of all, we need to have a way for getting our data out of a database into Flink. And this is exactly what I'm going to talk about. So Debezium, it's an open source project for log-based change data capture. And in a nutshell, it's really easily explained. It is about getting changes out of your database as transactions are executed there. So whenever there's a customer record inserted, a purchase order gets updated, or something gets deleted, you would like to know about that fact and you would like to react to that event. And the way Debezium lets you do this is by tapping into the transaction log of the database. So all the databases, they have this transaction log, which essentially is an append-only data structure. Whenever a transaction comes in, those operations will be appended to this log. And this is the canonical source of the data changes in our database. So that's it in a nutshell. So the database executes transactions. Debezium uses different ways, different APIs and formats for getting hold of that information, and then exposes those as change events to consumers, typically via Apache Kafka, but also you can use it with Amazon Kinesis, Apache Pulsar, or embed it into Flink, as we will see in a bit. Maybe, and I could go on and talk for hours about Debezium, but the one point I want to make is it is, so there's no standardized way for getting change events out of the database. So unlike JDBC or APIs in other languages, which allow you to get to your database and query it, there's no standardized API, no standardized format for getting change events out of the database. So the Debezium engineering team, or folks like Sergey working, for instance, on the SQL Server connector, they do all this original research and investigation to find out, so how do we get changes out of MySQL? How do we get changes out of Postgres? And so on. And then we take this information and expose it in a generic abstract format. So this means now that your event consumers, they don't have to care too much from which kind of database this event is coming from. Just to, kind of touch on your community slide. So Debezium also is an open source project. It's Apache license. So, there's no field of use limitation or whatever. You can use it in any way you would like. And actually, there's many vendors, many commercial parties who do that. Decodable being one of them, right? So that's the beauty of it. And now it does this thing, so going to the transaction log and extracting change events out of it, but then there's many more things around it. So for instance, there's this entire notion of doing initial snapshotting or backfills, because, well, if you start up your connectors, you won't have the transaction logs from last week in all likelihood, because the database itself, it will discard those transaction logs once it doesn't use or doesn't need them any longer itself. So the database would use them for transaction recovery. So in case things go wrong, we can get back to a consistent state. And for replication purposes, and once the database figures, okay, I don't need those specific segments of my transaction log any longer. It would discard them because otherwise our disk would just fill up. So this is where this notion of snapshotting comes into the picture. And yeah, there's web-based UI, all kinds of stuff. And really, it's battle proven. So there is huge deployments of companies with hundreds or thousands of Debezium connectors. Sometimes I'm really impressed how brave they are. So it's really, quite impressive actually. All right. So now let me talk a little bit about use case, because I think this is always the most important thing. So why would you want to use this kind of tool? And in my opinion, being able to react to data changes with a low latency, this is an enabler for your data, right? So I would say one of the most common use cases would be replication in the widest sense. So you would like to take your data as it changes from your operational database, Postgres, MySQL, and so on, to, let's say, an analytical data store, Apache Pinot, Druid, ClickHouse, or maybe BigQuery, Snowflake, those kind of things. So, and of course, you want to have your data in those analytics systems also as fresh as possible, right? So if you think about an real-time analytics store like Pinot, which is actually used for driving user-facing use cases, like, I don't know, dashboard. This data must be up to date. So you don't want to have data from half an hour ago in Pinot. You want to have your current data there. And this is exactly what you would get with low latency CDC. So just to give you an idea of the order of magnitude, for instance, I know of people who have large-scale Debezium deployments going from a MySQL cluster, they take their data through Kafka into Google BigQuery, and they have an end-to-end latency of less than 2 seconds. So within less than 2 seconds after something has changed in their operational database, they will see it in BigQuery, and they will be able to do any sorts of analytical queries on that data. So that's all replication. Then there's search indexes. So let's say you use something like Elasticsearch or OpenSearch to have full text search functionality for your data. Of course, typically full text search isn't as flexible in related databases. This sort of real-time data pipeline would allow you to update a search index or to keep a search index in sync with your operational data. Caching, another super common use case. I see it more and more coming. People would like to have caches or views of their data close to the user, maybe in some sort of edge location, so they can serve read requests with a very low timely overhead, in close proximity to users. So you need to update those caches after data changes in the system of record. And again, CDC would help us with that. Many more use cases, audit logs, and creating denormalized views of our data. Quite a few things. There's 2 things I want to show and focus on today, and this is like how we can take data from an operational database into a search index, and then how we can go about building audit logs. Now, as I mentioned, there is no standardized way for getting a change event out of a database. So it's not like we implement once Debezium and we would have CDC support for all kinds of databases. Instead, we need to have a bespoke connector for each database which we want to support. And you can kind of see the logos here, which are supported there. Like I would say, like all the prominent ones are there. For instance, one thing I'm super excited about is Google Cloud Spanner, which just was recently added. And this was actually developed by the Google Cloud Spanner team themselves. So we have different kinds or different categories of connectors. There's those what we call the core connectors. So they are part of the Debezium repo on GitHub. They are part of the Debezium release cycle. So you would always see those there. And also, I should say, it's developed by the Debezium, core community, which is mostly sponsored by Red Hat. So this is what's happening there. But then there's this notion of community-led connectors. So in this case, it's folks other than Red Hat. It's folks like Google, or it's folks like Stripe who work on the Vitesse connector. So they have this need for this connector, and they realized, okay, we would like to work on that as part of the Debezium umbrella. And this still is part of the Debezium GitHub org. It's part of Debezium releases, but then it's other organizations who work on that. And to be honest, this is like a long tail of connectors. So for a small development team, it's just hard to keep up with all of those subtleties of all those different APIs, which is why it's so vital that there is this large community of people working on that. And somebody like Google, I mean, they have the knowledge, they have the testing environment for something like Google Cloud Spanner, so it makes tons of sense for them to work on that. And finally, and most interesting, in my opinion, there is what we would call, I know, external connectors. So in this case, it's actually organizations like ScyllaDB or Yugabyte. They just realized, okay, Debezium is an interesting project. We would also like to have CDC capability for their databases, or for their databases. But they decided they don't want to be part of the Debezium release train. They want to develop a connector on their end by themselves. And this is what they do. So they just take the Debezium framework and then implement this kind of connector under their own reign. And let me see. Right, and just to drive home that point a little bit, so there's this post by some guy from the ScyllaDB team. So here they explain why they decided to base their CDC connector on the Debezium connector framework. You will find it if you go to.
I'm just trying to see who it is.
Oh, who it is? Are you ScyllaDB or?
I used to.
Oh, okay, I
was
see.
very-
It is Piotr Grabowski.
Yeah, Piotr.
You know him? All right, awesome.
One of the people.
Okay, one of the Piotr's.
We had like 5 people.
Oh, wow. Okay.
I know which
Right. And for them, the reason to do that is because, first of all, it gets quite easy for them. They benefit from all this filtering and portions of the snapshotting. And so they get quite a bit for free, but also then they expose exactly the same change event format as all the other Debezium connectors. So again, for a user, then it doesn't matter. Does this event originate from MySQL or does it originate from ScyllaDB, which is, of course, is nice because you always have multiple kinds of databases, and still you would like to be able to implement the use cases against those data feeds like in a unified way, right? So this is why it's so interesting that Debezium, I would say, and of course I'm biased, but I would say it's becoming a de facto standard for a CDC format. All right, so let's see, just jumping forth and back a little bit. So yes, touching on the format. So I spoke a lot about those change events. We should elaborate a little bit how do they look like? And in a nutshell, it's very simple. It just describes a data row which has changed. So if you have like a relational database, there, they have like a flat row record, and there's a before state and an after state of that row. So in this case, if it's an update event, right? So in this case, there was just this last name which changed. So it's the old state of the row, the new state of the row, and the schema there. This is representing the schema of your data, right? So it resembles exactly your table structure, and this is an important thing which we will come back later on. So that's the actual data itself, before and after. And of course, if this would be like an insert event, you would just have this after part because there's no old state for an insert record. And if it was a delete event, we would just have the before part. And then in addition, there's a bit of metadata as part of those events. So we have like, information what kind of database this was, like connector version, position in the transaction log, like offset information, timestamps, which table. For instance, in case of MySQL, we can give you the query which triggered this change. So all sorts of interesting metadata. And of course, also you have this op field, which tells you just what type of event this is. Okay, so this is change data capture. It's about getting data with low latency out of a database into the world. And by the way, I should say this most of the times is used with Apache Kafka and Kafka Connect in particular. So this is how people use Debezium. But there's other ways, and I will touch on that in a little bit. Now, the challenge is, okay, we have this change event stream. So all the changes of our customer data, let's say, and maybe we have something like a sync connector. So this takes this data out of our Kafka topic and puts it into a BigQuery or whatever you have. But very often this is not enough. You would like to do some changes to this data. So maybe you just want to filter your data to, adjust like dates or date formats or your names or field names. Maybe you want to do some join of multiple change event streams to express like a higher level aggregate of data. So just taking the raw data feed typically isn't enough. And this is where Apache Flink comes into the picture because it allows us to do stateful stream processing on those change event streams. And I would like to, first of all, just give you like a high level intuition what you can do in terms of operations on change event streams. And then I will dive a little bit deeper into some specific use cases. So the first one, it's quite simple. And this would be pretty much the same you could do with Kafka Connect. If you are using that, you have a source connector which takes data from a database, and then you have a sync connector, which puts your data elsewhere. So just a simple data pipeline from A to B. You wouldn't use Flink typically if this is all you want to do. But as I mentioned, most of the times people want to do a bit more. So in the first step, you would just to do some sort of stateless transformation of the data. So you want to filter your data. So I mentioned converting date formats. This comes up all the time. There's all kinds of different date formats. You would like to, go to one canonical format. So doing this sort of transformation is very useful. Maybe you have sensitive data. Maybe you have, I don't know, particular columns in your source schema which you don't want to expose to the outside world. So we'd like to remove them from such a change event stream. So that would be like, another kind of mapping. Maybe there's just specific kinds of records. I don't know. Maybe you have like B2C and B2B customers, and you only would like to expose one of those two kinds. So you could filter out the other kind. Maybe you want to encrypt your data, all this kind of stuff. So that's all stateless transformations, which, reasons about events one at a time. So we can do those things like encryption, masking, filtering. We can do those just by looking at a single event, doing a little bit of transformation to it, or maybe just discarding it, otherwise sending it out. Just look at single events. What else can I do? I can think about routing my events. So maybe, again, coming back to this B2B and B2C use case, maybe depending on the type of my customer, I would like to send this data to different data warehouses. So I could implement a routing functionality in Apache Flink quite easily, which would do this sort of content-based routing. I could have all different kinds of things. So there's a very rich ecosystem of connectors in Flink. So there's support, of course, for Kafka, for Kinesis, all those streaming platforms, but also for all kinds of databases like MongoDB, Elasticsearch. Is it the database? I guess it's fair to say, I don't know. Is it the database? What do people think? Let's call it the database. OLAP store. It's used. Okay, let's agree. It's used as a database. The jury is out, but that's all right on it. Apache Pinot as a real-time OLAP store, Snowflake, S3. So very often people just have this use case. They just want to take their data and put it to S3 for archival purposes. And then I ask people, how do you go and access this data? We never do it. We just are obligated to have it somewhere. So, okay, so that's what you do in S3. You can do it if that's what you want to. So, that's just my way of saying there's a rich system of a rich ecosystem of connectors, which, allow you to implement data pipelines towards all those kinds of different systems. Enrichment. So that's the one I'm always curious about. So sometimes you have a change event which just isn't fully self-descriptive. So for instance, in case maybe you just need to go to another system and just get some data, some reference data, which you would like to put in your change event. So maybe, I don't know, you have a currency code, and I admit it's contrived, but let's say you have a currency code coming in as part of your change events, and that you would like to enrich this with the exchange rate at this particular point in time. So you go to another service to make this call to get the exchange rate and put it into change events. Or sometimes change events coming from a database like Cassandra, they are not fully they are not complete. They would just give you the modified state in case of an update. So you wouldn't get the columns or the fields, not sure what they call it in Cassandra, which haven't changed their value, but maybe you would like to send the data, you would like to take the full state of a row and send this out to a sync system. So you need to somehow materialize back this missing state, which you don't have when just looking at this partial update. So you could implement this sort of enrichment functionality by means of adding a state store to such a data pipeline. And then we have all those use cases which involve multiple change event streams. So you would like to join your data. Maybe you have this use case where there is like IoT data coming in from a Kafka topic, like temperature measurements. You would like to enrich this with reference data about the weather stations, which you then get in from CDC. So you could implement this kind of join. Or maybe you have just persisted your domain model across multiple tables, which is a very natural thing to do, right? So in a relational database, let's say you have purchase orders, there's purchase order headers in one table, purchase order lines in another table. So this is like a one-to-n relationship, and you would like to join those two tables together or in this case, those two change event streams together to have an entire representation of the purchase order with all its lines. So that would be joins. Okay, before diving a little bit more into some of the use cases, I want to do a little detour and talk a little bit about how we can use Debezium in the context of Apache Flink, because there's a few interesting options. So I mentioned already Kafka Connect. So Kafka Connect, is anybody using Kafka Connect, by the way? Say yes. Okay, a few ones. Okay, so it's a part of the Apache Kafka ecosystem, and it's a runtime and a development framework for connectors, source and sink connectors, for taking data into Kafka or for taking data out of Kafka into an external system. And bluntly speaking, Debezium is a set of Kafka Connect source connectors. And this is what I would say is the majority of people definitely how they use Debezium. But then we realized, okay, people like the capabilities of Debezium, and I'm sure they also like Kafka. I don't want to say they don't like Kafka, but maybe they have some other messaging infrastructure. Maybe they are like a Google Cloud PubSub shop, and they still would like to use Debezium. And this is where this notion of Debezium server comes into the picture, because essentially in your overall architecture, it has the same role to play as Kafka Connect. So it's the runtime for the Debezium connectors. But then instead of sending data to Kafka, it gives you connectivity with all kinds of messaging infrastructure like Kinesis, Nuts, Pulsar, whatever have you, Hazelcast, something Hazelcast, I forgot it. But you know, so all kinds of messaging infrastructure you could use with the Debezium server to take your change events into those kinds of messaging infrastructures. And then there's what we call the Debezium embedded engine. And this is, I would say, the most flexible, most powerful way of using Debezium. In that mode, you use it as a library embedded into your Java or JVM-based application. So you use it within your own process. You register essentially just a callback method, which will be invoked whenever a change event is received. And within this callback method, you can do whatever you want. You can print it out to the command line or to the standard output. You could send it elsewhere. The Debezium server is based on this embedded engine, so it gives you the full flexibility. And I'm saying this because there's this project called Flink CDC, which is essentially a set of Apache Flink connectors, and they take the Debezium embedded engine essentially and make it available to Flink, right, as a native Flink connector. So you don't have to stream data first to Kafka. You just run it within a Flink task natively in Flink itself, in the Flink process. And then you can consume those change event streams with Apache Flink. All right, so how are we doing on time? You saved so much time. I can go on for hours now. Right, so let's talk a little bit about use cases. Again, I think that's the most relevant part. What can we do with all those tools in our box? And the first one I would like to elaborate and demo a little bit is audit logs. So, very often we are obligated to keep a history, a log of all our data as it changes. So like, this custom record got created and we do like several updates to it, and our purchase order at some point it got like fulfilled. And we would need to take this data, keep the complete track of changes so we can go back and analyze the data or look for failures. Maybe police is coming, they want to see what's happened in our database. So we need to keep an audit log. And if you squint a little, such a change event stream is some form of an audit log, right? Because it has the complete history of our data. So if we were to take this change event stream, we just put it into Kafka, keep indefinite retention, and then we'd have some sort of audit log, or we put it into a database and we would have that. But what's missing is typically the metadata which describes the context of the data change. So like, what was the user who did this data change? Maybe their client IP address, device identifier, like a use case identifier, all this sort of metadata. And typically we don't store this sort of metadata within our actual business tables, right? We just have our core data there. So the question is, how can we enrich our change events with this sort of audit relevant metadata? And to give you one idea, what you could do is, and this is specific to Postgres, but you could also implement it similarly for other databases. So the idea is, at the beginning of each transaction which you execute in your database, you you provide that metadata. Now you could just insert that metadata into a particular table, but actually with Postgres, it's even more interesting because what you can do there is you can write information straight to the transaction log, and it will never show up in any table. So you just can write arbitrary contents to the transaction log. That's pretty cool, I would say. So the idea is we use this function called PG logical emit message, and we say, okay, you know, this is our metadata, like client date, use case identifier, username, and so on. So that's the content of this metadata. It's up to us what this should be. Then there's this a type. So I say this is all that data, and I just use this to differentiate this from other kinds of logical messages. And finally, this true parameter, this means this should be a transactional message. So this means if our transaction gets rolled back, then this record also wouldn't be written. So we can insert the data into the transaction log, and well, then we, of course, we want to put it into our actual change events. And this is now where we enter the end of stream processing, because if we look at our transaction flow, so this is what we could do, right? So we have a begin transaction. So we start a transaction, then we insert our metadata using this function to emit a logical decoding message, as it's called. Then we go about our business. We do whatever changes and inserts and updates and deletes we want to do in our database. So in this case, some inserts, and then we commit this transaction. And then, sorry, I would use Apache Flink with this Flink CDC project to actually take this metadata and put it into my change events. And this is what I'm going to show you. So I have a few things running there, and somebody said we should use Minikube, I believe. So I'm going further below. I'm using Docker Compose. Okay, so I use Docker Compose, and I have a few things which I'm starting here, like a database, you know, then Elasticsearch. I will use this later on. So just a little bit of infrastructure, so we have something to play with. And now, in this case, I want to implement this use case just using this data stream API. So it's going to be like a Java programming job, essentially. Now, let me also go to my database there. So I have this MySQL database. I want to say use MyDB. All right. Now, what I want to do is, and I don't want to bore you too much with my typing, so I'm going to copy this. First of all, actually, I want to go to my Postgres database instead of MySQL. Sorry about that. Let me get out here again. Let's go there. MySQL is coming later. Now, what I'm going to do is I just create a simple table called data. By the way, is this big enough? Can you read it in the back? It's all right. Yeah. So I'm just going to create this table data. There's just a primary key and then this text column. And the other thing I'm going to do is I change the replica identity of this table to full. So this means now if I use Debezium to get the changes from this table, it will actually have the full state of the row and also the previous part or the previous state in case of an update. So this is what this replica identity is about. So I've created my table. Now, let me see what else I want to do. Yeah, I can now insert some data, but first of all, let me show you my stream processing job. And yes, I'm the last person on this world who uses Eclipse. So this is, I confess to that. But this is what I'm going to use here. And as Robert mentioned, in the most simplest case, I can just run my Flink job. I implement my main method, and I run this from my IDE, which is great for testing. Or if you are at a meetup, at a Dremio office, this is like what you want to do. And here, I use this API for getting changes, first of all. So I set up an instance of this Postgres SQL source. I specify my host name, credentials, and so on. And that's pretty much it. Don't have to care too much about all the other stuff. So I have that. And now I want to process my data. And for this, I'm now using this API, which would give me all those operators like filtering, grouping, aggregating, and so on. In this case, I'm just using the flat map operator. And this essentially has the semantics when an event comes in, it may emit either non-event, one event, or many events. So it takes something in and it might emit something or nothing, or even multiple things. And now this function, this is my ordered metadata enrichment function. So that's the one I implemented here. And now just to give you a high level intuition of what happens here, So this gets now invoked for every change event which comes in, and we have this operation discriminator. So you saw that before. And now in this case, if it's M, like a logical decoding message, then I know, okay, this is one of those special events which are just written to a transaction log. So I want to look at the prefix, it's the audit type. So that's the one I'm interested here. So if I have this kind of event, then I just want to take this data, like its content, and write it into some sort of state store. So Flink provides me with the capability to persist state. So I take the metadata, put it into the state store. And otherwise, if I get a, and by the way, I should say, each and every event contains also the transaction ID. So I specify essentially that, that's the state for this particular transaction with a given ID. If it's not one of those M events, then it's like an actual event, like insert, update, delete. So now in this case, I go to my state store and I just make sure the transaction ID is the right one. And then I take the data from the state store and propagate it into my change event. And then I emit it using this collect call here. All right, so that's pretty much it. There's a bit of more infrastructure, but that's the gist of it. So let me run this. And again, usually I would deploy this into a Flink cluster. In this case, I just run it from my IDE. Now, the first thing I want to do is I just want to execute a transaction here. So just 2 simple inserts. Let me do this. And now if I go to my job there, by the way, the output of my pipeline, I just print it to the standard output here, right? So now I can take a look there. And here I see those are those changes as we have seen them before, right? So see, it's create events, some metadata, and I have this state there. I don't have the metadata because I didn't provide any metadata, right? So that makes sense. So let me execute another transaction. And now in this case, you already see it, I do provide the metadata. So I start my transaction, I call PG logical emit message, just some arbitrary metadata, and then I do my my business. All right, let's commit that one. And now if I take a look, I see, okay, those change events now, they have been enriched with this metadata, which is the same for all the events in this transaction. And now this looks more like a transaction log, right? Because I have the data changes themselves, but also the metadata. So that's one way for going about implementing such a audit log use case. Any questions so far, by the way? Robert, please.
What are the performance implications of using this full replication mode for database?
What are the performance implications of using the full replica identity? I don't think there is really a significant performance implication. It uses more the disk space because it needs to bake all the information into the transaction log events. That's the main reason why people sometimes don't want to do this.
Our DBA doesn't like.
Your DBA does like, yes. It's, and what's that?
It burns out, yeah.
Yes, right. Exactly. So it's a trade-off. I mean, if you are just fine with like new state, that's fine as well. But yeah, you need to figure out what you want and what your requirements are, right?
I've got a follow-up
Sure.
Same question. What if the people who already had a database didn't have that, so the full replica?
So if you have an existing database, yes. I mean, so now we touch on the human side of this. I mean, I like tech. Now we have this human factor, the problem is, yes, so this is a conversation you need to have, right? So you need to talk to your DBA. Your database needs to be configured in a specific way. Like in the case of MySQL, the bin log must be row format. For Postgres, you may want to do some configuration for, I don't know, for Oracle, you need to provide some crans. So yes, there's sometimes there's a little bit of tension and people want to understand why this needs to happen. But then typically if you explain why you want to do it and what's the motivation, what's the benefit of CBC, what's the value you get out of it, then an organization can get behind it.
It's a pretty uphill battle for that. Like, for example, I was in charge of the GoPros before joining NVIDIA, so I was in charge of GoPros data infrastructure for almost 6 years. So this is one of the use cases that I wish I had something I didn't notice.
Right.
So I would have probably introduced, but the production database will not just say, oh, let's upgrade there.
Yeah, I mean, sure.
Because we're taking the data for analysis.
Right. Yes.
analytics can wait.
I see. Yeah, I mean, there's different ways you could look about it, right? I mean, one way, for instance, also you could, and maybe this is how some folks would start, you could stream changes off of a replica in a database. So you could, and actually now, for instance, with, this always was possible with MySQL, with Postgres, it's possible now, just since version 16, you can change streams from a read-only replica. So maybe this gives people more confidence, doesn't touch our production database just yet. But to be honest, I think those concerns are usually a bit over the top, and yeah, it's a matter of socializing this and getting everyone on board.
And I think often you're actually reducing the load of the database because you're offloading analytic workloads into a system that's specialized like Flink instead of running an analytics workload on your transaction database.
Right. That's another good point for sure.
We like in Copper, we did reading from the replica, not from the production. But I actually wouldn't use this. Because in that case we have to write a big Spark jobs and they're running snapshots from the even for the replica just to repeat it so we can capture some changes.
Okay, yeah, that makes sense. Cool. Any other questions? If not, let's keep going. Let me talk a little bit about another. Well, we were just talking about concerns. So I'm in the concerns department now. Let's talk about another concern. And the concern is, does this kind of change data capture break our database encapsulation? So my friend Chris Riccomini, he, for instance, wrote this blog post. It does break encapsulation. And the concern is understandable, right? Because, well, if we go to our database and we expose the raw schema of our tables, now what happens if we were to change the schema of our tables? So we were, I don't know, we modify the name of the column or its type. I mean, it's quite uncommon, but let's say it's type or like do cardinality change. Now, this means if you have consumers on those change event streams, you may break them, right? Because now actually we kind of make our data model an API of our application. So that's a valid concern. Now, the question is, how much of a problem is this? I mean, I would say here it helps to think about all this in terms of, the boundaries of the contexts of like domain-driven design and what are the boundaries between different domains. So let's say my use case is caching. I just want to take the data from my operational database into a cache. I would argue I would like to have the same structure there because this is just another view of my data. So here I would not be concerned. But maybe if I push this data over to another team, they're sitting at the other end of the hallway, I talk to them like once per year. In this case, you want to have some more stable contract than your internal database schema. I would totally be on board with that. So I totally stole this visualization from this very good blog post. I recommend to read it. So, this is what happens. People change their schema definitions. They have this other team. They don't know about it. They are not on board. And suddenly the analytics import stuff breaks and, everybody's unhappy. So how can stream processing help us with that? Well, it can help us by establishing stable, well-defined data contracts. So the idea is instead of exposing those raw change event streams to the outside world, instead we create like an indirection. So we create consciously designed schemas with, with all the types and names as we want them. And this is our user-facing interface. And then we use stream processing to essentially map this raw table stream to that public data contract. And this gives us now all kinds of advantages, right? So let's say maybe we really want to make sure that we don't expose any fields which we don't mean to expose. Now, if I just were to add a column to my source table, this would be part of the change event stream, the raw change event stream. But if I have this consciously designed data contract, well, unless I also add this new field there, then it would be part of the incoming stream, but it wouldn't be part of this public stream. And same, let's say we rename fields or we change their type, this kind of thing, then we could implement some sort of transformation to take the data and make it adhere to our public contract. And of course, we would use things like a schema registry to define and manage those contracts. And then we would use tools like Flink, and I don't know what this other logo is there. but we would use Flink to implement our stream processing job for taking the raw data and make it valid against this public contract. Again, there's this great blog post from Chad and Adrian. They are like old-time Debezium users as well. They wrote about that, and I also want to write about it on the decodable blog. Right, as I mentioned, having this indirection, it gives us the flexibility to design what are the columns which we want to expose, what names and types, data structures. Maybe we want to, again, if you have this like one-to-n kind of relationship, but in our public contract, maybe this should be like a nested structure. So we could use stream processing to materialize that and expose the data that way. And of course, also now we can change our schema, right? So let's say a rename is happening, but we could really easily implement a stream processing job, which now takes the new field of the internal schema, but maps it back to the old public stable name in our downstream stream. So that's data contracts. Now, I want to do another demo, and this touches a little bit on the use case, which also Robert introduced in the beginning. So we want to take data from our operational databases, like in this case, it's MySQL and Postgres, into a search index, Elasticsearch, so we can do full text search on our data. And just for the sake of the example, here I have essentially two databases, three tables. So I have a products table, I have an orders table, I have a shipments table. The latter lives in Postgres. So I get 3 streams in Flink tables, as we will see. Then I can join them and I can write them out into another table in Flink, which then takes the data to Elasticsearch. And I want to do this not using the bespoke programming, which I did before with the data stream API, but in this case, I want to do it using SQL. So I put my data engineer hat on, and I want to go about this in a declarative way. All right, so let's do it. Now, let me go to my cheat sheet again. I have that one running. So now I want to go to my MySQL database. So let me get out here. All right. I want to start up a Flink cluster now. And in this case, it's just a single Flink node running on my computer here. So let me do this. And now this Flink version is still, let me go here. Right, this Flink version is still not working with Java 17, it's Java 11. So I just want to make sure I'm using Java 11. This looks good. All right, so let me start this cluster. All right, and now this starts Flink on my machine. Again, it could be Docker, Kubernetes, whatever, but actually this runs now locally on my laptop. Okay, what's next? I want to get now an interactive shell on my Flink cluster. So to run some queries against it. So there's this SQL client which comes with it, and this allows me to run interactive queries against Flink, which is great for development purposes, right? So this allows me to iterate on my queries in an ad hoc interactive fashion. The first thing I want to do is I want to create this table, and we've seen this already before. So this represents now this connection, and you can see it. It's the MySQL CDC connector. Again, my credentials information there, and this table represents now this change event stream. So we will see this reflects the reality in my database as data changes. I need to specify a schema. So this resembles the schema of this orders table in my MySQL database. So let me create this. And now if I do a select against this table here in Flink, I should see the content of my table in MySQL. So let me actually go back to my MySQL shell. So if I do here, I use MyDB, so I want to use the right database. Now if I do select star from orders, so I have the same data here. Now let me actually do an insert. So you see that actually the view in Flink is live. So I insert another one. And if I go back to my Flink shell, I already see, okay, I have now this 5th record there. Just for the sake of the example, let me do some change. So let's say I want to, update orders set, what is it, customer name to, I know, Brian, where order ID equals 105. All right. And again, now I see, okay, this also has been updated here. And I see the current state of my data within Flink. So that's pretty cool, but it's not too exciting yet, right? Because it just is the view on one data. It's getting more interesting if I now define queries on the data, and that's what I'm going to next. Before I do that, though, I also want to create the table definitions for my other streams or for my other source tables, let's say. So I create one for the products table. So again, this is in my SQL. I have that one. I create one for my shipments table. So this lives in Postgres. So I'm going to use the Postgres CDC connector. And now I actually can join and combine data coming in from multiple databases. I think that's pretty interesting. And now actually I could start and do a select and join and all that. But to save some time, I actually create another table which takes the result of the join. So this essentially has now the entire set of all my columns from my 3 tables, like orders, products, and shipment data. And now in this case, this is using this Elasticsearch sync connector. So this is about taking the data. Whenever I insert something into this table, it will be written into Elasticsearch. So let me create that one. At this point, I have all my connections in place. Now I need to define a query which executes this join and which takes the data into Elasticsearch. Or I should say into that other table, and then the connector will take the data into Elasticsearch. So let me run that insert. And again, I'm going to copy this. It's just too much for me to type. But as you see, I just take my orders table, I do a left join on the products, I do a left join on the shipments, and I insert all that into this enriched orders table. So I define this data pipeline just by defining this sort of insert statement. And now, as you see, I don't get back this interactive query result over here, but instead it says, okay, I've deployed this job onto my Flink cluster. So what I can do now is I can go actually to the web UI of my Flink cluster and take a look at this job which has been deployed here. So they have this web console coming there. So this is the previous job which I canceled, and I have this one running now. And I see like its topology, like what's the parallelism. If there was back pressure because too much data coming in, I would see all that. I could take a look at the exceptions and checkpoints and all this kind of stuff. So I have this job running in Flink now, and I could operate it, or I could take a look at it. But I hope it's running just fine. All right. So what I want to do next is, well, I actually want to go to Elasticsearch and see whether my data has arrived there. So I'm just taking a look at the web REST API and Elasticsearch. I see I have those 5 records overall. So this is just the number of documents in that index. And to see that this actually works, let me insert some more. I'm going to use a few different product categories. So I did 3 more. So now if I go back to my index, I should see now that the number of records has been updated. And indeed, I see, okay, I have now 8 indexes in my document. Now, admittedly, the volume of data changes is real low here, but this allows me actually to keep this index in sync with this data in my operational databases in really a low latency. Now, the last thing I want to do is actually, I want to just show you that you now can also reason about or work with that data. And for that, I'm just going to Kibana, and I'm just quickly going to create a dashboard to give you a bit of a feeling of how quickly this can actually work. So for that, I define an index pattern. By the way, by no means I'm a Kibana expert, so I know enough to be dangerous here, but I want to do this index pattern, and then I can actually go and say, I want to create like a new dashboard, and there, let me make it smaller, create visualization. I refer to my index there, and the horizontal axis, I want to have my product category. Okay, this looks good. Let me close that. And on the vertical axis, I just want to take the count. So I have the orders by category, and I see how many orders I have per category. So I get this nice dashboard. And again, let me do a few more inserts there in my source database, a few more purchase orders, and now I should see, that this dashboard gets updated. So let me refresh it, and I see those columns change. And I hope I could bring the point across quite easily. I can implement this sort of dashboard functionality on this real-time stream of change event data. All right. So I think we're on the home stretch. Yes, I wanna keep going a little bit with that use case, because I mean I kind of cheated when I showed this data model to you. I had this flat representation of my data. I just had an orders table, a shipments table, and the products table. But really, this isn't how purchase orders would be modeled, right? It would come back again to this model of I have one table with order headers, another table with order lines. So this would probably be more realistic. And then it would look like here on the left-hand side, I would a foreign key relationship between those two. And this is essentially how a purchase order would look like in reality, as it's modeled in a relational database. Now, the challenge I have is, if I want to put this data into a document store like Elasticsearch, I want to have the data from one purchase order, or aggregate in terms of domain-driven design. I want to have this entire structure in a single document in my search index. I don't want to spread this across multiple documents, because then it's just not how you would design things in Elasticsearch. So the data structure I would like to have is like on the right-hand side here. So I have this nested structure which has this array of order lines. And now this entire document, this describes my purchase order. And now the question is, how can I go about creating this sort of document structure? And well, as is with Flink itself, as of today, I cannot really do this very well, I would say. But what I can do is I can essentially implement, I mean, I can do it with Flink, of course, I should say that. I can do everything with the data stream API, but not with Flink SQL. But what I can do is I can define a custom function, a user-defined function, or UDF for short. And now I could use this function for essentially taking the end side of my join and converting this into an array. So this is what I'm doing here. So I have this array aggregation UDF, which I implemented myself. And now I can express this entire thing as a single query there, because, well, in this case, I'm using a correlated subquery, but it also could be a join. But really, the Flink type system, the Flink SQL type system is so flexible that it allows me to do those things. So I can say I want to have a row for the order lines. I want to aggregate those rows into an array. And this should then be part of my order structure. And if I were to serialize this into JSON, it would look like here on the right-hand side. And just briefly to give you an idea of how this UDF would be implemented, it's actually quite simple. So all which happens is you keep track of the records which should be accumulated into one purchase order. So essentially, you just could focus on those two functions: accumulate, which gets added when a new record on the end side comes in. So you just add it to some state store. If there's this retract function called, you would remove it. So this would be called, for instance, if you were to delete one order line. And then there's just this get value function, which takes the value from the state store. So really, it's just about taking the elements from the menu side, putting them literally or figuratively speaking into an array, and then managing the state of this array. So it's quite simple. And then you would just register this UDF with Flink. In your table definition, now coming back to the type system, you would say, okay, this lines field, it should actually be an array of rows with this particular structure. And that's pretty much all there is to it, right? So we have seen the query already. So then you would use this array aggregation function to emit the data adhering to this schema which we defined before. Oh yeah, shameless plug. So I explored all that. If you want to learn how it really works, you can go to the Decodable YouTube channel. I did a data streaming quick tip, episode number 3, which describes how to implement this kind of UDF. All right, and so how are people feeling? I have one more thing. Are you like, you want to go home, or I can talk like about one, or like thumbs up, thumbs down? Okay, thumbs up. Those people who didn't move their thumbs, you've lost. Okay. So let me talk about one last thing which is close to my heart, and this is about making or creating awareness for the transaction boundaries in our source database. Because if you look at this kind of data structure here with this nested JSON here, So in my source database, if I were to create this purchase order, those inserts would happen in a single transaction, right? So we would do the insert in the purchase order table, and then we would do the inserts into our order lines table. We would commit the transaction, and this would be an atomic operation. But from a Flink perspective, if we receive those change events on those for those different tables or streams, I have lost the awareness for those transaction boundaries. So what could happen is I run this join or this array aggregation, and it would run first for the first order line. So I would produce a purchase order with a single order line. The next order line event comes in, I would run the same aggregation logic again. I would emit the array with 2 elements. And then the last event comes in, so I would emit the entire structure. Now, depending on our use case and the requirements, exposing those intermediary events isn't desirable, because, for instance, if I were to put this data into Elasticsearch and I do a query in a bad moment of time, then I would get like incomplete search results, right? Because I would just have parts of my data in my search index. So ideally, I would only emit the data to Elasticsearch once I have received all the events from this transaction, and I know now I can run this aggregation. It is going to be complete, and now I can send out this data. And this is what Debezium lets you do by means of transaction metadata. So all the change events, as you see them here on the left-hand side, they have information about the transaction, like ID and like in offset within this transaction. And then there's another topic or stream which you can subscribe to, and this tells you about the transactions. So it tells you when a transaction starts, but more interestingly, it also tells you when a transaction commits, and in that commit event, it tells you how many events there were, and also of which kind, how many events there were. So in this case, in the example before, in this commit message, I would say there is 1 order header event and 3 order line events. And now I can use the information to correlate those things together and essentially implement some sort of buffering logic and only emit this aggregation result or whatever I'm going to do once I've received all the events from one transaction. No worries, I'm not going to show you how to implement this because I haven't done it yet, but there is this blog post, from Flink Forward. So who was it, Stripe, they implemented this, and it's something which we want to do in Decodable to provide this functionality out of the box. So you then, I know, by means of a SQL keyword, we will have to see how we do it. We would say, okay, this pipeline should emit events adhering to the transactional guarantees of our source database. So I think this is super interesting. All the primitives are there. Robert and I, we did already some brainstorming how we could implement this, and I think it will be a really cool feature to have in Flink at some point. All right, so with that, we're pretty much done. Just coming back to the beginning, I hope I could convince you, yes, we want to have fresh data, so to implement all those kinds of use cases, dashboarding, search indexes, and so on, and really want to have current data there, right? And we get current data there with tools like Debezium, which give us low latency change data capture, and we get data there in the format and representation we want by means of Apache Flink and doing stream processing there. And now, of course, we didn't really touch at all on the operational complexity of running all this, right? So running Debezium, I guess you can speak to that. Running Debezium can be challenging. Running Flink for sure can be challenging. You need to think about provisioning your hardware, sizing VMs, making sure it's up to date, making sure it's secure. You want to have like role-based access control, monitoring, observability, all this kind of stuff. And this is my long-winded way of saying, all your life can be much simpler if you use all this via a managed service. And I happen to know a company which provides all that as a managed service. Yes, a few resources. So Debezium and Apache Flink, they're on Twitter or X, as I heard it's called today. You can find the examples which I showed on a decodable repository on organization, and the examples we put there on GitHub. And Robert, your picture is missing, but you should be here. Yes. So that's pretty much all we had. And yes, we would be open for questions.
Thank you. Thank you.
This company is called Decodable. Yes, for the record, let the record show.
So speaking of the operational aspect, I saw your MySQL password in the presentation. Is there a way to
I'm going to change it after the presentation.
and then after that, is there a way, to pass it to the connector in a different way rather than, typing in the table definition?
Yes. So how is it with Flink SQL? Do you know, is there secret support?
So I think there's some tooling in Flink that removes it from like logs and so on.
Right.
So,
But technically, no. Right. Like that's how Flink does it.
yeah, I'm alluding to something like data providers in Kafka Connect where you can source the
Right. You have to connect
credentials
the
from
secret
somewhere,
provider.
like from a file or something.
I don't think that there is. It's like,
Yeah, not in vanilla.
not in the.
In decodable, for example, we use like a different authentication provider that doesn't require us to pass in like a plain text password. So we retrieve the secret also through different means.
Right. So if you were to use this managed experience, there would be like a secret service, secret facility, so you would avoid that very much.
What we do under the hood basically is a complex dance of using like a secret store, like in AWS, like a hardware-backed secret store. And then there's like this complicated dance of getting Kubernetes to like reference it and mount it and like all the.
So it
all
all
the
happens behind the scenes.
Yeah. And so like that's like the correct way to do it, so that you don't have.
Right.
This particular. Or you can just pick your passwords.
My question was about the performance implications on the joins there within Flink, because obviously it was very quick because you had a table of 4 elements or something. What are there things within Flink to optimize that? Are there functional limits as to how big of a table you want to try to do joins within Flink before you start running into issues? Talk a little bit about.
Right. Oh, I think that's good.
Yeah, so basically you're completely right. You need to replicate the entire state of your join. I'm going to go closer to the microphone. So you need to replicate the entire state of your join into Flink, into the Flink internal state store. So that's your limiting factor. Like how fast can you?
Is that in RAM or that's disk?
Exactly, that's the thing. So you have these pluggable state backends in Flink. You can use a memory state backend, then it's RAM, or you use the RoxyB state backend, then it's disk. Like RoxyB is using like an on-disk LSM tree on your local SSD to store the state of your join. So if you have like 100 gigabytes in your table, you will have 100 gigabytes in Flink state in RoxyB, which will do like on every event that is coming in, it will do a lookup in RoxyB to make this join and emit the result. At Decodable, we have customers that are running at a really large scale, like many joins, many tables. Yeah, like we have a customer that has like 17 tables that they're CDCing from, have like a big SQL statement that describes this join.
But then how are those being updated? Are those also being updated by, like, once you pull the table that you're joining to, is that also being updated through the Debezium protocol to keep it up to date?
Yes, correct. So basically, Flink is subscribing to the transaction log of the database.
Right.
And whenever there's a change in any of the tables, it will emit a change event that is consumed by Flink and is updating the state, like the RoxyB representation of this table. So basically, we're mirroring the state from the database into Flink so that it can perform this real-time join. Whenever there's an update, it will emit a change event downstream.
But you're functionally keeping an entire set of that. You're keeping that entire database in RoxyB or in RAM. Yeah.
It depends. So if you're doing a count aggregation, for example, we just keep the count per key, for example.
Okay.
So Flink is smart enough to figure out what's the minimal amount of data I need to keep to make this efficient.
The query planner has some sort of basically pruning logic, like typical sort of relational algebra shenanigans. And the scaling properties on it, because like Robert showed the sort of distributed nature of it, it's effectively a partition hash join, right? So like each individual worker has a slice of the larger key space that is then like partitioned over many machines. Then, depending on the.
And there's many tricks that we play. Like the state is compressed on this, if you're able to be regularly compact this data, like clean up trash. And we do incremental checkpoints, and we don't have to upload the entire 100 gigabytes every 30 seconds or whatever checkpoint frequency we have. So we only upload the data that has changed since the last checkpoint, like an incremental backup, basically. There's lots and lots of tricks that we do to make handling very large state efficient. So at current, the Netflix team told me that they have jobs with like terabytes of state for these workloads.
Yeah, that's just gonna ask next. Is you're talking about 100 gigabyte, which is great, but a data platform that's, a small side cable, right? I mean, at terabyte scale or something, it's expensive, it's functional,
It's relatively inexpensive in the sense that because the actual storage system of record for Flink state is S3, which is like cheaper than like EBS or something like that. The actual runtime infrastructure can simply be NVMe, like ephemeral disk in the cloud. And so you're not paying for like system volumes and like provisions, like, whatever sort of infrastructure. And like, so it's really just got to be an instance type that has locally attached NVMe. And like, depending on sort of the size, now you might blow out more machines. But again, like this is only in the case where like you're performing a 17-way join and projecting all fields, like which typically not super common in comparison to some of the other stuff. There are sort of elements that sort of get into how to sort of further reduce that state size, and keep in mind that this is per job. So in certain cases, you're not necessarily, like you might have 1 or 2 or 5 of those big jobs, and then there's like everything else, which is effectively trivial. So in the smallest case, Flink state is simply the Kafka offsets or something like that. So it's, okay.
thank you.
Any other questions?
As for scaling, let's say you have like a Flink cluster deployed via an operator, and you create, let's say, new queries or new jobs or new something that requires compute resources. Does the operator take care of scaling the infrastructure behind it, or needs to be done sort of separately manually?
Okay, so your question is about scaling the infrastructure when your workload is changing.
Yes.
So the Kubernetes operator has an auto-scaling facility. So it allows you to, it will monitor the how busy the operators are, like the individual Flink operators are, and will scale the cluster accordingly.
So is it based on like CPU usage, something like that?
No, this is based, so there's a research paper how to do this, and this is a Kubernetes research paper, and this paper is measuring the number of unprocessed records in the source. So if you're reading from Kafka and you know that you have like 10 million unprocessed records, and you know that you're processing 100,000 records per second right now, then you can basically do some math, how many more instances of this Kafka source I need to be able to read this input faster, and then it will also do some approximation for the downstream operators, like the window operators, application operators, and so on the throughput, and then scale them up accordingly as well. So that's how the Flink Kubernetes operator is solving auto-scaling. You can also solve this in a different way. So you can also use, for example, the horizontal pod auto-scalers in Kubernetes, monitor the CPU utilization, and then adjust the number of task managers accordingly. Like you want to make sure that the CPU is always at like 6%.
So and when the horizontal pod autoscaler spins up new pods, will Flink react to that and will redistribute its workloads?
I like that you used the word react because it's called reactive mode. So basically, it's a special scheduler within Flink that is always grabbing as many resources as they have. So if you're giving Flink more resources, like more worker nodes, Flink will scale up the job.
And there's more modes that you can use for this, but that's my recommendation. To use the reactive mode, and then you can scale up and down as resources are there.
Anyone else on this side? No? All right. With that, I want to thank Gunnar and Robert for the great talk. It's a great discussion from the audience, and of course, thanks to Decodable to show up with 50 people. So, thank you.
So thanks for being here. There's some Flink stickers, aka Flickers. There's Flink stickers there, and of course, if you have questions or if that, please reach out to me or Robert at Decodable. But still, now, yeah, okay. And we are very happy to discuss all your streaming needs. Okay.
We'll
Asking questions online.
yes, I don't know what.
Oh, there's a chat. Oh man, yeah. You've been on mute. We gotta redo it.
Oh, and chat.
Start over. What was that first part? You're muted.
Okay, so
I can't hear you.
so one.
Okay, so the first question is, are you connecting Debezium to Oracle Golden Gate?
So no, there's no connection. They are competing. I don't know. They are in the same field of solutions, right? So Golden Gate would be Oracle's commercial CDC solution for Oracle database. Debezium also has a CDC connector for Oracle database. So they're, different solutions for the same problem.
Okay, the second question is, how do you compare with how do you compare this with the Databricks CDC with downstream processing?
Wow. What is this Databricks thing? I don't know. Do they CDC? I don't know.
Yeah, so I think what this is referring to is what's called Delta Live tables, right? Which is basically a version of Delta that supports changes within the Delta Lake data set. And so that is once the data has been written into Delta, you have the ability to sort of process changes, throughout. And I think Iceberg has support for this these days, and I think Hootie is getting support. So like all of these systems sort of have this behavior. I think the primary difference is that is once the data is landed in the data lake or the data warehouse, whereas what Gunnar is describing is getting it out of the original database of record, Cassandra, Celia, whatever the right system there is.
Okay, I hope that answers your question. And then, okay, and the next one is, how do you handle the schema changes on the source? Databricks CDC uses Arrow, which is good for schema changes.
Right. So schema changes. I mean, I was trying to allude to that a little bit with the data contracts part, right? So there would be one way to go about it, to establish a separate stable contract and then map your raw streams to that contract. I think that would help. There's things like schema evolution rules in schema registries, like Confluent ones, like the one from Confluent, where you could, for instance, just disallow specific kind of breaking schema changes. But to be honest, most of the time, I think it's about adding fields, which typically is like not a problem. Adding tables, of course, again, isn't the problem. Yeah, I don't know. Eric, do you want anything on schema? It is like our favorite question.
Yeah.
It's like usually it's the first one.
It's the first one because it's real, right? Like it happens. But generally speaking, I think relational database schema evolution rules apply. Adding things is okay as long as downstream stuff is okay with that. But like renaming fields, dropping fields, or changing data types, like unless you're a sociopath,